All right, welcome again. At this point, we want to look at another non-parametric test, which we call Friedman test. This is equivalent to one-way repeated measure ANOVA. One-way repeated measures ANOVA. And this comprises of more than two dependent samples or groups. Now, in previous ANOVA, we have two dependent samples. All right, but in this one, we have more than two dependent samples. When the samples or groups are more than two and they are not meeting the conditions or assumptions for parametric tests, then we have to switch over to non-parametric test called Friedman test, which is a one-way repeated measures. So in this case, let's run our tidy fast. So I love to attach my tidy fast always, so that in case I want to use some piping and the rest. Now, we want to understand that the Friedman test is actually an extension of the Wisconsin signed rank test. We have done that before. If you go back again, you see that there is an extension because that one is doing with two samples. Okay. Now, the non-parametric analogy and analog of one-way ANOVA repeated measures is what we are talking about here. So, Friedman test is used to assess whether there are any statistically significant differences between the distributions of three or more paired groups based on median. Now, we are looking at three or more paired groups. That is a Friedman. So most time we look at two paired groups, okay? Two paired under ANOVA. But now we're looking at three or more paired groups. So we are using Friedman for that. So it is recommended when the normality assumption of one-way ANOVA repeated ANOVA measures test is not met. All right, that is when we use this. Okay, if you cannot meet the assumption conditions for normality check for one-way repeated ANOVA, so we use Friedman normal parametric test. All right, so there are two methods to test this particular to perform this testing. Two methods, and the first method is based on your data set. All right, the data set arrangement, which I will show you the two, how it works. But sometimes the data set may be collected in different ways. Maybe the way you collect it, maybe you collect them differently because they are the same they are the same specimen, but they are repeated for each different section of responses. So you have to know how to arrange data properly. So to illustrate the first method, we will create or curate a data set that shows the reaction time of 5 patients on 4 different drugs. Right? See 5 patients and yes, on 4 different drugs. Since each patient is measured on each of the 4 drugs, we will use the Friedman test to determine if the mean, right now this is median, now not this now, if the median reaction time differs between drugs, because Friedman is median based, okay? It's not mean based. It's using ranking, okay? To use median to rank. So it's we want to determine if the median reaction time differs between drugs. So we want to create data set first. So this is our data set we wanted to create. All right, it's just very simple. Just say this is a person 1 to 5, repeat 4 times. Then we have the drugs 1 to 4. We have times 2 times 5. Then we have the scores pass here, which is 20. So we can run this line of code. So we have our data here. All right, so we can let's glimpse it. Let's glimpse it and see our data how it look like. All right, so we have person, we have drug, we have score. 20 rows, 3 columns. Okay. So we are assuming that this data does not meet any assumption for parameters. Even the number of observations is even 20, so it's against all odds. But nevertheless, we are going to do our non-parametric actually. So we are, if you see 1, 2, 3, 4, 1, 2, 3, 4. This is person now. This first person, this second person, this third person. All right. So we are having 5 people now, right? Or 5 persons. All right. So for the drug applied to them, you have 4 drugs. Okay, 4 category of drugs now: drug 1, drug 2, drug 3, drug 4, drug 1, drug 2, drug 3, drug 4, and the scores is given here. All right, so this is just our data set to use. So this is a repeated measure now. Repeated measure, the drug is repeated. So this is different from two peer groups. Okay, two peer groups is almost the same actually, but this one is more than two pair now. Okay, this is more than two pair, so you can see that it's more than. So let's create a box plus now and let's see what are the structure of data. So we have a drug 1 to 4. You can see drug 1 to 4. This is this categorical variable, even though it's not categorized here. I mean, our table here. We can just do that. Okay, you can do that. You can just factor it by ourselves. Okay, which I did here. You can see I factored drug here. It's supposed to be factored variable, so I have to apply that here. But you can do that also in your other coding, so that you can just do it up and factor it up once and for all, so that you'll not be factoring everywhere. So, but let's just do that as a minor. But looking at this now, you can see that the median is not the same, right? It's not the same. So even though we have some applier here and here, 1, 2 here, so we can also view on the summary of this, and from here we have a drug 1, 2, 3, 4, count each of them 5 times. We have median. This median is not the same, 26, 28, 30, 30, and our RQ is only the same for this and this. Each other ones are different for the median. So this is our just a summary of our data set. Okay, what we are looking at. So you can see to understand that the median differ actually for each drugs. Okay, differ. But I want to show you statistically that is it just a by chance, or statistically it is significant that the median differ for uh, each drugs, all right, for the score. So let's perform the test. To perform a Friedman test, you just call Friedman.test. We're passing our say y equals to data dollar score. If you I think you attach our data, you just say score here. Okay, our data I don't think it's not attached. So then we pass our group data here, which is drug. All right, don't forget our group data is drug. You can see here it's drug. Okay, our score is our numeric data, so score. So the blocks is person. So don't forget this framework takes 3 parameters, not like the other ones. This one we have score, we have a drug, we have group data, we have y. Okay, it's equal to this is y axis. That's our response. We have group. The groups is equal to this one, which is called our categorical variable we have here, right? And we have blocks. The block is person. Each person set. So each person, but that's a block. So these are the 3 things we needed to run this. Okay. Okay. So if I run this now, let's run this and see the result. Okay. Friedman rank sum test. We have 0.0357, which is 0.034. This is significant. All right. Is significant. You can see our result here. Our chi-square is 3.56. Our degree of freedom is 3. We have a perfect result here. So this is so we can say that the chi-square test statistic is this 3.56, and the corresponding p-value is 0.034, because this p-value is less than 0.05, which is our threshold. We can reject the null hypothesis that the median response time is the same for all groups, all 4 groups, all 4 drugs, which is our group variable. So we can reject the null hypothesis, which means they are not the same. Actually, we have seen before in our summary, but we don't want to conclude based on that. We want to do proper testing to confirm. So we have sufficient evidence to conclude that the type of drug used lead to statistically significant difference in response time. All right. So that is simple. But we want to also perform some ad hoc tests here. We do advanced investigation. So because the Friedman test tells us if there are differences in median response time across the drugs, it does not tell us specifically which drug have different median response time. We don't know. So to figure that out, we need to conduct post hoc tests. The pairwise constant rank sum test, which we have done before with we can use either Benjamin or Bonferroni adjustment for p-value. Okay, so anyone we want to perform can also use none if they are too stringent for us. Okay, so that is so we perform the post hoc test here. We call it a pairwise with constant test. We just pass our score here, our drug here, then our p-value adjustment we will be either correction for Benjamin or for Bonferroni. There are more. There are Holmes. There are BY. There are different type of FRD, FDR. So many adjustments you can use, and you can use none if you don't want to. That is if they are too stringent for us. So let's run this and see what I'm talking about. Don't mind the warning here, okay? Don't mind the warning. So here we have pairwise comparison using recursion rank sum test with continuity correction. So we have you can see that here we have in only this 3 4 column 1 2 3 1 2 2 4. So this is only one that is a okay, that is significant. This is significant because at this point now we are using correction. Okay, this adjustment of p-value, not real p-value. Okay, so we can consider this one significant at this point. All right, if you want to confirm that, we can just change it to none to use our original p-value. Okay, and that should be the best. Okay, at this point, because of the stringency of the let's just say we say none. All right, you say none. Let's first see. So this produces. Let's first see this result first. This produces a matrix that shows the p-value for each pairwise Wilcoxon rank sum test. We can see that the only drug groups that have a statistically significant difference at 0.10 are groups 3 and 4. Right? 3 and 4, which is 0.07. Okay. This one have significant. Only this one. You can see that. All right, so but we can further remove this none. Okay, if you remove this none now, for example, I mean, if you put none there, you can see that this one is significant. Now you can see this original p-value, this one also significant original p-value, this and this. Okay, you can see that groups 3 and 4. Now we have group 3 and 4 and group 2 and 4. All right, that are now significant now. Okay, when you use original p-value. All right, so this is just the first method. All right, but the second method is when your data is collected differently. So we are going to use data set from Datarium, which we have used before. Just run Datarium, run this, we are going to use self-esteem data, and we are going to let's first glimpse it and see the result. Okay, this is our data set. Okay, we have ID. This for each person. Okay, each person. All right, 10 per row. So we have look at the way data set is collected now. It's collected differently. That's what I'm saying. So the other one were collected together, but this one is collected differently. Set by set, time was collected differently for each of the person, not together like the other one. So if you run like this now, let's say we run the first thing, you can see ID here, T1, T2, T3. So this T1, T2, T3 is essentially our group. Okay, our grouping. But this one is the score for each of them. Score for each of them. Score for each of them. All right, for each person. All right. So this is what I'm talking about. So if you say let's look at the first 20 and see what I'm talking about. So you only have 10. You only have 10 here. So you have more than 20. Total you have is 10, not 20. Okay, you can't go 20 because even though we have 30 observations, okay, we have 30 observations, but you can only see by 10 because they are collected differently. Okay, for each ID person, we collected this one, collected this one for this time, for this score. All right, so this is kind of what I'm talking about. If data tests come in this form, you can also compute in this form like this, or you can convert it to the method 1, which we just used now. Right, so and let's attach our self-esteem now. Okay, let's attach it. So now that we understand this, that data set, how it look like now. Okay, look at it now. We have T1, T2, T3. This is a different time. Okay, this is our ID person, individual person. All right. So what we do is that we have to create a matrix of a sample matrix. Okay, so that's the first thing we do. So we combine them into matrix. This T1, T2, T3 to matrix, this 3 to matrix. All right. That's what we do. Then we create the matrix, and we now use matrix to run the Friedman test to have our. So this is our sample in our line we are going to use now. We say T1, T2, T3, which for each of them. So if this time, the other one we have drug. Okay, don't forget. So that, for example, if you have here maybe that one D1, D2, D3, for example, now drug 1, drug 2, drug 3, drug 4, D1, D2, D3, D4, like being like this as well. Okay, but we don't. That one was collected together, which make the work easier and straightforward. But this one is not like that. All right, this one is different. It's collected differently. So you can use this method T1, T2, T3, T3. The total number of columns is 3. If there are 4, you say 4. If there are 5, you say 5 here. So just run this line. Okay, run this line. So it is wrong. It's assigned to sample now. We have a sample, no sample now. We are going to pass that one to our Friedman test here. So we run this. So we have our result p-value equal to what? 0.001117, which is highly significant also as well. So we can actually combine the time together as score and use previous method. So this one that we use now, okay, we can change this one to this particular sample. We can change it to previous method 1 by combining it together. All right, then we can now use the method 1. Don't forget we got 0.001117, right? So let's try that. You can install RS statics here at library, so that it will help you to work together. Let's say we use piping. Say gather function from this particular library. We want to key our time score. So we 1, 2, 3. So this 3 will convert to ID time. Then we can just look at the first 10 sets. All right. So let's run this together. All right, so we have done that now. We now have a self-esteem now data set, right? So let's look at the first term first. Now look at it. We have our ID, time, and score. So that T1, T2, T3 is time, right? But now we have combined them together now. As you can see, you can have this score. So this is what we have before here. All right, you can see what you have before here, T1, T2, T3. But in this case, they are in different column. This is a different one. So we're now to combine together. You can see this one with this one with this one with this separately, collected separately. So now we are now trying to arrange them, all right, into different forms. So you have 1 to 10. Okay, if you run 20, we have you see what I'm. Let me change to 20 and see what I'm talking about. Okay, look at it now. We have 20 row now. Total is 30 row. Total is 30. All right. So we have 1 to 10 here. Okay, for T1 time 1, we have 1 to 10 again for time 2, time 1 to 10 for time 3. If you continue to 30 rows, so you can see that is a repeated measure, right, for each person. So for example, now if for just 2 pair now, you can now say okay 1, 2. Okay, this one you are seeing now is just a pair. Okay, 1 pair, 1 and 2. Okay, but we are dealing with more than 2 pairs now, 2 or more pairs. So we have 1, 2, and 3 sets now. The same specimen, the same subjects, the same persons. That's what I'm trying to say now. It's repeated here again for each time. It's okay, and the third time as well for each person. So the same person now. So that is called pair, which we have done before in ANOVA. So we are doing multiple groups of multiple measure here now. So let's try and run this ANOVA on this again. Now that we have created our new self-esteem now in this form, like the former one we did before, we want to use that method now. We can now create it now. Don't forget we got a 0.000111 here when we use a matrix method because of our data structure. Now we can now use the same method here. We are using a method 1 here now by calling this y is equal to self-esteem @ score, which our score is this. Okay, We now pass our groups also here. Self-esteem time is our time with the group. Okay, our ID is block self-esteem ID. That time it was person we use, so this one is ID. You can see here. So for each person, so we can run this now. Okay, and see the result. See the result. We get same thing. All right, we got 0.00000117, the same thing. So, and we have the same degree of freedom and the same chi-square. Can you see? Look at it. You can see. So, no difference. But the data set structure is not the same. So we have to convert it to get to use the method 1. But just in case your data set does not come in this form, that is what I'm trying to let you know, so that you can, if you come in this form, don't be dismayed. You can just use this matrix method straight and pass it to Friedman test. It's very easy and very simple. Okay, but if it comes in this form, or if you want to see convert to the previous method, fine. So if you come in this method, this one previous one come in this form, I think you are good to go. Just run it and go. Right? If the data set come like this, okay. If you come like the first one like this, if you come in this form, you have no problem. Just run it using first method. But if it doesn't come, use matrix method, and you are good to go. So that is just that for now. So you can see performing your ad hoc if you want. I mean ad hoc test if you want. So it's still the same. So no problem. So I think we is more clearer now. As we have explained. So don't forget what we got as our report, and how you respond to this result here, report we got here. So I will see us in the next class as we look at another method in the parametric. So thank you so much. I mean non-parametric rather. Thank you so much for listening. If you are not yet subscribed, you can do that so that you can continue to enjoy more of the videos. I will see you in the next class. Goodbye for now.